Hello everyone. So this stream should be starting up. Yeah, there it is. Alright, so today I want to learn about ownership in the Rust programming language. And it says here ownership is Rust's most unique feature, and it's what enables Rust to make memory safety guarantees without needing a garbage collector. Therefore, it's important to understand how it works. So I'm excited to learn about this because I've heard that ownership is well, here it's saying it's the most unique feature, and I've heard it's a very neat concept and powerful. But first, I did promise that I was going to mention whatever was interesting from the common programming concepts, and there was one thing that was interesting in the functions, and this was its discussion concerning the difference between statements and expressions. So this is a statement, right? It's an assignment. We're assigning 6 to y. And really, and what it's saying is that a statement does not have any sort of return value. And so you cannot let x equal this, right? Because this doesn't return anything. Like this won't return 6 for x to be assigned to. And this is in contrast to C, where you can do x equals y equals 6. And so here a statement is returning something that x can be assigned to. In Rust, you don't have that possibility. But, and also, so that's a statement, right? It doesn't return anything. But an expression does. And if you notice, expressions by themselves do not have a semicolon afterwards. And so here in this block, we say let y equals, and this is a block. And you notice the block has the ending semicolon because this whole thing is a statement. But within the block, we have one statement, and then we have an expression, x plus 1. And x plus 1 returns, in this case, 4. And this is what's returned from the block into y. And there's also a line where you simply have the expression 5, and this pretty much returns 5 because this is an expression and it's within a block. So this function is defined to return an int, and the block in which it's defined simply returns 5. So yeah, that was an interesting discussion. And so here's a function plus 1 where you have a parameter x, and it returns an integer, 32-bit integer, and it takes as an argument or as a parameter a 32-bit integer, and then it returns the result of this expression. And this would be an error because this is not a statement, right? And also, well, this is not an error per se. The error that it produces is that function is expecting 32 or an int to be returned, and this does not return anything. It is a statement, right? So implicitly returns, so the function implicitly returns empty, an empty tuple, but is expecting an int because you've written this as a statement as opposed to an expression, and the difference is the semicolon. All right, so now that we got that, we'll understand ownership. All right, central feature, and it has deep implications. All right. So like in the previous one, I'm going to just simply comment when I find something to point out or to really comment about. I'm not going to read everything, but I'll highlight what I am reading. yeah, so some languages have garbage collection, like Java. Other languages must explicitly allocate in free, like C and C++. Okay, so Rust does not rely on a garbage collector, nor do you need to explicitly allocate in free. And it does this through implicit compiling checks through a feature called ownership. Alright, so we'll be working with strings. So stack and heap are both volatile memory, volatile. Could be stored in, let's say, cache or DDR. RAM, that is. Yeah, so the stack stores values in the order it gets them and removes the value in the opposite order. So this is referred to as last in, first out. Like a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. So I have, you know, let's say this is one plate, 2 plates. So okay, this is going to be the bottom of the stack, and I just put one there, and then I put another. You put another plate on the stack. I put another and I put another plate on the stack. Put another plate on the stack. Oh, but then I need to remove them. I removed this plate, so now we have the rest of the stack here left. And then if I remove another one, I remove this one, so now we have 3 plates left. But then I can add another, so then I add the 4th. And yeah, so you can't add or remove them from the middle or bottom. And adding data is called pushing onto, and removing is called popping off. So we pop the top off on the stack, and we push onto the stack. And it must have a known fixed size. And data with an unknown size at compile time, or a size that might change, must be stored on the heap instead. It is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer, which is the address of that location. So the pointer is the address, and what it points to is the actual data that you will be using. But for now it's empty because we haven't actually put any data. So this process is called allocating on the heap, and is sometimes abbreviated as just allocating. So we're allocating memory, and we request a certain amount of space from the heap. So if we, let's say we request this many characters from the heap, right? So the pointer is going to point to the location of this, because in this article you have all these other spots that have been taken up, or that just we didn't happen to reserve in our call. And then we say, okay, I want to be able to store this many characters. So then you request a memory partition of this size, and then if the operating system reserves it successfully, it points to the first location of it, and then you can fill these with whatever characters you want or whatever data you want. Okay, pushing values onto the stack is not considered allocating. Alright, so the process of reserving memory in the heap is called allocating. Pushing values onto the stack is not considered allocating. Because the pointer is a known fixed size, the pointer from the heap that points to whatever initial starting point of the data, because the pointer is a known fixed size, you can store the pointer on the stack, but when you want the actual data, you must follow the pointer. So think of being seated at a restaurant. When you enter, you state the number of people in your group, and the staff finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you've been seated to find you. Right, they ask the staff because they are the pointer. And because the stack is more fixed, it's faster to push onto the stack than it is to allocate on the heap. But the heap is more flexible. When your code calls a function, the values passed into the function, including potentially pointers to data on the heap, and the function's local variables get pushed onto the stack, because when we define a function, especially in Rust where it's obvious that you have to define the type of the parameters, it knows exactly how big that's going to be, and so it can push it onto the stack, even if the size, even if it includes pointers, even if some of those parameters include pointers to if it includes pointers to data on the heap. And the Rust's ownership addresses all these problems. But knowing that managing heap data is why ownership exists can help explain why it works the way it does. Okay, so this is the point of ownership. Ownership exists so that we can manage heap data. Okay, so the rules are each value in Rust has a variable that's called its owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. Simple enough. Alright, so I think at this point it will behoove us to set up a project so we can we'll do it in a bit. I think when we do a project, like an actual project, let's say an IO project, then we'll open up. But from here we can just understand what they're saying. So yeah, we'll keep to the browser right now. Alright, so let's say we have this. And so S refers to a string literal. And this variable is valid from the point at which it's declared until the end of the current scope. And so when we have a block like this is the scope in which this is valid. Right. And because it's not yet defined here, it's not valid to refer to it here, but since we define it here or declare it, we can use it, and then we can use it here afterwards until the end of scope. Right, so when S comes into scope, it is valid, it remains valid until it goes out of scope. And this should be familiar, like it says, if you're coming from other programming languages. Now, let's figure out the string. Alright, let's check out the stream, make sure it's okay. We'll go to the end. Yeah, so it's running along fine. Cool. Right, we've discovered the immutability of, well, by default, of all variables in a previous, the previous stream. Okay. Okay, so a string literal is fixed and immutable, but the string object is allocated on the heap and as such is able to store an amount of text that is unknown to us at compile time. You can create a string from a string literal using the from function like so. So we have the string type and we call the from function that's associated with that type, and we specify hello to initialize a string called hello. Well, the string that has hello as its value. And this can be mutated. And so here we're pushing onto the string, comma world, and we'll print hello world afterward. Okay, so the string type implies that it is a mutable, growable piece of text, and even then, perhaps you can shrink it, right? It's probably a growable and shrinkable piece of text, and so we need to allocate an amount of memory in the heap unknown at compile time, and this requires the heap, and so this means the memory must be requested, and we need a way of returning this memory when we're done. Yeah, and we handle the requesting, but the second part of the way of returning the memory, usually it's saying it's handled with a garbage collector, like in Java. Well, with some languages, it's a usual modern practice to use a garbage collector, like let's say JavaScript or Java, and it keeps track and cleans up memory that isn't being used anymore. We don't have to think about it. But without it, it's our responsibility, like in C. And so we would have to explicitly in languages like C or C++ return the memory and keep track of it. And it's been a difficult programming problem historically. Yes. The memory is automatically returned once the variable that owns it goes out of scope. There's a version of our scope example using a string instead of a string literal. So before we had the example, and it's identical, except we are using the string type instead of a string literal. And it's called automatically. This drop function, which handles the deallocation, is called automatically when the scope is ended. Alright, so multiple variables can interact with the same data in different ways in Rust. Let's look at an example using an integer. So yes, this code we're saying is saying bind the value of 5 to x, and then we then make a copy of the value in x and bind it to y. We now have two variables x and y, and both equal 5. This is indeed what is happening because integers are simple values with a known fixed size and thus are on the stack, and these two 5 values are pushed onto the stack. So there are indeed two copies because I suppose we're using the stack. We're using simple literals. And this would be the same, I suppose, with a string literal, right? Because that is also fixed at compile time. But when we have the string type, this is mutable, this is immutable. And so this mutable string is going to have different rules, I suppose. Let's see. And yeah, it's saying, but this isn't quite what happens. So something different is happening than here because this is mutable, whereas this 5 is not. It is immutable. Okay, so this is the composition of a string. So a string has a pointer, a length, and a capacity. And that pointer points to the heap, and that heap has reserved for it 5 spots, and hello is bound to those 5 spots in memory. And this is saying is stored on the stack, and this is stored on the heap. And length is how much memory the contents of the string is currently using. So this can change, but it's a fixed size. Like this is an integer, let's say a 32-bit integer, and so it can be still allocated on the heap even though this value can change, because it's whatever this value is, it's always going to be a 32-bit integer. And so that's why you can store this on the heap. And the same thing for capacity. Not sure what capacity is. I suppose capacity, maybe length is how much of the capacity is actually being used. Like let's say we shrink this by 1 and we say, okay, it's hello has now become hell. And The capacity is still 5. We still have 5 indices to work with, but the length of the actual string has been reduced to 4. So that could be the difference. Or maybe vice versa, but I'm not sure. Okay, so what's happening when we copy, right? So the capacity is the total amount of memory so the length is how much memory in the bytes the contents of the string is currently using. The capacity is the total amount of memory that the string has received in the allocator. So yeah, that's what I just described. The difference between length and capacity matters, but not in this context, so for now it's fine to ignore. When we assign S1 to S2, the string data is copied, meaning we copy the pointer. So when we copy S1 to S2, we copy this on the stack. So this is assigned to this, and this, S2, is being copied from S1, and S2 is a copy of whatever S1 had on the stack. But the pointer is an identical copy, and so they both point to the same index on the stack, the same data on the stack. And we do not copy the data on the heap. I'm sorry, this is the heap. They both point to the same data on the heap. But when the copy is made here, it's the stack object or the stack struct that is copied. Right. Rust might have perhaps done this style of, might have implemented this for this operator, but they decided to go for this because this could be very expensive. So earlier we said that when a variable goes out of scope, Rust automatically calls the drop function and cleans up the heap memory for that variable. But figure 4-2 shows both, this one right here, it shows both data pointers pointing to the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as a double free error and is one of the memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure memory safety, there's one more detail to what happens in this situation in Rust. Instead of trying to copy the allocated memory, Rust considers S1 to no longer be valid. And so at this point, S1 has gone out of scope. So therefore, Rust doesn't need to free anything when S1 goes out of scope. Check it out. Check out what happens when you try to use S1 after S2 is created. It won't work. You'll get an error like this because Rust prevents you from testing the invalidated reference. Right. That makes sense. So here, S1 is valid, but once so is it any mutable object this rule applies to? We'll see. Okay, so it's not that S1 goes out of scope, it's that S1 is invalid, and when both S1 and S2 go out of scope, Rust knows that only S2 is valid, and so will only free memory associated with S2 on the heap. So I suppose if any type has memory allocated on the heap, that's when these rules are applied. And does that mean any mutable object? Is it tied to the heap? I don't know, because let's say we had a let mutable I1 equal to 5, right? That is known at compile time what size that's going to be. So you don't, even then, if it's mutable or immutable, I wouldn't expect Rust to need to use the heap for that memory. You can still use the stack, right? Because stack is just a pointer to an object that you can either push onto or pop off of, and so you can change what the stack is pointing to. I think maybe not. Maybe if it is mutable, maybe any mutable type will be allocated to the heap. I'm not sure. We'll have to keep on reading. Okay, Rust will never automatically create deep copies of your data. And a deep copy looks like this. Any automatic copying can be assumed to be inexpensive in terms of runtime performance. If we do want to deeply copy the heap data of the string, not just the stack data, we can use a common method called clone. Okay, so this is a deep copy, and we can then using this method, both of these strings will be valid. And it produces behavior like this. So that's a deep copy. And it may be expensive, like I said up there. So this works and is valid. Okay. But this is immutable. So it's not, it might not, this discussion might not address that question. Let's see. Okay, so types such as integers that have a known size at compile time are stored entirely on the stack, so copies of the actual values are quick to make. That means there's no reason we would want to prevent x from being valid after we create the variable y. There's no difference between deep and shallow copying here, so cloning wouldn't do anything different, and we'll just leave it out. Okay. So all of these types. All right, let's read about the copy trait. Rust has a special annotation called the copy trait that we can place on types like integers that are stored in the stack. If a type implements the copy trait, an older variable is still usable after assignment. Rust won't let us annotate a type with the copy trait if the type or any of its parts has implemented the drop trait. Right, because drop is associated with the heap. And copy assumes that the type can entirely be stored on the stack. So these two are incommensurable with each other. The type needs something special to happen when the value goes out of scope, and we add the copy annotation to that type, we'll get a compile time error. So what types implement the copy traits? You can check the documentation for the given type to be sure, but as a general rule, any group of simple scalar values can implement copy, and nothing that requires allocation or some form of resource can implement copy. So allocation onto the heap. And so here are some of the types. So integers like U32, floating points F64, Boolean types, cars, and tuples, because these are all, well, tuples that only contain types that also implement copy. These are all things that are known at compile time. I'm still interested in what a mutable integer would do, because all of these are, this is immutable. Here, I'm curious now, so we're going to we're just gonna do a quick test. So we'll go to workspace, code, cd rust lang book. We'll go to variables, and then we'll do code dot. Don't need this. All right, so let mutable x equals 5. And then we'll do the print line of x is x. And this, of course, is a state. This is a statement, so it needs this. Okay, and then we'll let y equals x. And then we'll copy this for y. And then we're going to do cargo run. And we will so let's try to do this. And so let's just say x equals 6. We'll put this right after. Okay. So mutability does not affect this literal beings, or rather this being being stored on the stack. So mutability does not affect it. It's simply whether the size, whether I32, or rather the type of x and y, the size of this is known at compile time. And for a mutable string, for the string type, it is not known at compile time, but for a string literal, it is. Can I have a let mutable x equals, let's do hello. Let's say x equals what's up. These are both literals. You have mute. And then we'll say let y equal x. And then we'll do this for y. didn't save. Okay. Okay, so we can't change x when it's mutable, which makes sense. Well, when it's immutable, which makes sense. Okay, I think I'm starting to understand. So let's say, how did they do it? So it was something like string from hello. Alright, then we get an error because y has borrowed x, or y now owns what x previously owned. Right. Okay. This won't change anything. Makes sense, because this really only cares about x. Doesn't really apply to borrowability or ownership. So mute or the lack, so mutable or immutable doesn't really have anything to do with this conversation. Okay. That makes sense. And then we can do, let's state clone. And then it works. Yep. All right, cool. I'll leave this open for us. All right, so ownership and functions. The semantics for all right. S comes into scope, so this is main. So as S is used in here, so once the function takes ownership of S, it is no longer valid once the scope of this ends. Interesting. And because this is known at compile time, because this is not allocated onto the heap, but this one was, but this one wasn't, and so this 5 can be used afterward. Interesting. Okay, so S1 gets some string, so this gives ownership of some string to S1. Okay. Alright, so S2. So let S3 takes and gives back. Aha! So this takes ownership of a string, which happens to be S2, and then returns a string. And then S3 takes ownership of that same string. So this, whatever was S2, so S2 cannot be referenced here, but S3 can be referenced after. But here, it goes out of scope. S3 goes out of scope, and so cannot be referenced after here. Okay. Okay, so taking ownership and then returning ownership with every function is a bit tedious. What if you want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again, in addition to any data resulting from the body of the function that we might want to return as well. It's possible to return multiple values using a tuple, but this is too much ceremony. Luckily for us, Rust has a feature for this concept called references. So here, let's say this calculates the length, and so the function is s, which will end up taking ownership of s1 that we've allocated from the heap onto the heap here. We let length be the length of it, and then we return s in length. We don't have the return keyword here, but because it's an expression, fn implicitly assumes that this is what wants to be returned. And so we can assign the tuple s2 in length to the return of this. So let's look at references to see what we can do. So the issue we had in 4.5 is that we have to return the string to the calling function so we can still use the string after the call, because the string was moved into the function. So now we're going to learn about references. So here we define something that is onto the heap, that's pointed onto the heap, or allocated onto the heap. And then we'll use the same function here, which, well, it's a little different because instead of a string, s being a string, it's a reference to a string. And so it returns just the length. It doesn't return a tuple of both the string itself and the length. And so then you can just say let length equal calculate length of a reference to s1. And this is what a reference looks like. So this is the reference. It's just a pointer that points to s1, and then this pointer is what actually points to the data on the heap. Right, and so in the function definition, we have a reference to string, not just string. And because pointer is known at compile time what the size of pointer is, its use size, and remember in the previous stream, this is the size that depends on the system architecture. So in a 32-bit system, this would be 32 bits in size. In a 64-bit system, it would be 64 bits. And so because this is known at compile time, it's allocated onto the stack, or it's actually pushed onto the stack, and because of that, the rules that we were exploring involving the literals applies to it, and so it doesn't it doesn't have to. There is no transfer of ownership of something that is exclusively on the stack and makes no use of heap memory. The opposite of referencing by using ampersand is dereferencing, which is accomplished with the dereference operator star. We'll use some uses of the dereference operator in chapter 8 and blah. Alright. So here we're allocating onto the heap, and then we're letting length equal calculate length of a reference to S1. Alright, this syntax lets us create a reference that refers but does not own. And because it does not own, the value it points to will not be dropped when the reference goes out of scope. This is strange. I would feel like this is not the right, because this S is a reference to a string, so how is it that the reference, which is S, doesn't have the dot, there is no length property, I would think. I don't know, maybe there's something special going on with the pointer. Okay, so we cannot, so okay, this idea of having a reference as a function parameters is called borrowing. But because we never have ownership, we cannot modify. So here, this won't work. So function change some string, which is a reference to a string. I would have expected that you have to dereference, because this is a pointer to a string, right? Some string is a pointer to a string. I would have imagined that you had to dereference some string in order to call a method that's associated with string. Maybe Rust already infers that because it's a reference to a string, you want to dereference it, and so it automatically does it. It's a little odd. And so references are immutable. Okay, so you can So there is such a thing as a mutable reference, and this is what this is. That means that S can be changed, right? But there can only be one of these within any scope. So here it's saying, you know, if we let a mutable S go here and here, you'll notice that we have S being mutable as well. It's not just the reference that's mutable. If you look up here, it wasn't mutable. Anyway, when we have a mutable reference, there can only be one of them within the scope. This will give you an error. And this has the benefit of preventing data races at compile time. So when we do this, we can have multiple, but not simultaneously, because you can only have one per scope. Okay. And you can only have so you can have however many regular references you want, immutable references, but you cannot combine a mutable reference and an immutable reference. Okay. Multiple immutable references are okay because no one who is just reading the data has the ability to affect anyone else's reading of the data. Note that a reference's scope starts from where it is introduced and continues through the last time that reference is used. So this will compile because the scope of a reference, they're saying, is the last point it's being used. So at this point here, these references are out of scope. And so this will compile, even though, or it's not, yeah. Okay, so let's see, dangle. So what is a dangling pointer? A pointer that references a location in memory that may have been given to someone else by freeing some memory while preserving a pointer to that memory. So the function dangle returns a reference to a string. Let s, so here we're creating a string inside of this function, and then we're returning a reference to the string. But once this goes out of scope, which is here, this is going to be dropped from the heap, and so this will point to nothing. And so if we were to actually use this, the return value of this, it would be a dangling pointer, because this is automatically dropped at the end of scope. this function's return type contains a borrowed value, but there is no value for it to be borrowed from. Yeah, this is what I was saying. All right, these are the two rules. All right, let's look at this first. No dangle. The solution is to return the string directly. Right, because when we return something that has heap memory, it transfers ownership. Makes sense. If we look up here, that's what we were doing. Was it up here? No, it was in this 4.1. We looked at the end of this. We were looking at examples where it takes and gives back. And so a string is transferring ownership to S3. Okay. Now we're going to look at slices. So the slice does not have ownership. Okay, so this function is pretty much going to take the first word of a string, and that's found through white space. But what should we return? So we want a reference to a string, but what is it that we want to return? Okay, so instead of returning some type of a part of a string, we're just going to return the index of the end of the word. And this uSize is the pointer size. And okay, so we let bytes equals s string as bytes. I'm pretty certain that Rust automatically dereferences an argument if that argument is a reference. I'm going to look that up. Does Rust automatically dereference an argument with ref? There's a chapter. Okay, so then we'll defer this to that chapter. Okay. Alright, things are going well. Nice. Just hanging out there. Cool. Alright. Okay, so we have bytes as the string as bytes, and then for I reference the item in bytes.iter.enumerate. So I guess bytes.iter.enumerate is giving us both the index of the byte in this array and the reference to that gives us the reference to that location of the byte in the array. Okay. So it's a tuple of that. And so if the item is equal to a space, then we return I, which is the index. Right. Okay. And if this doesn't happen, then we just return the length, which is going to be that makes sense. Okay. Because this implies that there is no white space, right? So it's the whole thing. We consider the end of the word as the space. Okay. We're returning a usize on its own, but it's only meaningful. But it's only a meaningful number in the context of the reference to string. Right, because it's okay. In other words, because it's a separate value from the string, there's no guarantee that it will be valid in the future. Okay. Consider the program in listing 4.-8 that uses the first word function from listing. So we let the mutable s equals the string, and then we let the word equals the first word of the reference to s, and it'll get the value 5, which corresponds to here. And then this empties the string, making it equal to nothing, an empty string. Word still has the value 5 here, but there's no more string that we can meaningfully use the value 5 with. Word is now totally invalid. And this would fairly be a logic error. This program compiles without any errors and would also do so if we used word after calling s.clear. Right, we could use that value 5 with the variable s to try to extract the first word out, but this would be a bug because the contents of s have changed since we saved 5 in Word. Right, if we did a second word, then we would have to track both the starting value and the ending value, or ending index. What's the solution to this? String slices. So this is going to be a slice from 0 to 5, and this is going to be a slice of a string from 6 to 11. Okay. Right, and starting index and ending index is going to be it's going to be inclusive here, but exclusive here. So when we define 11, it'll actually go from 5 to 10. Or I'm sorry, from here it will go from 6 to 10, even though it says 11. And the logic behind it is that 11 minus 6 is 5, which is the length from 6 that we want. And so this is just them doing the same thing here, but dropping the 0. And if you want to go to the end, you can just drop the length or the ending. If you want the entire slice of the string, you just do dot dot. Okay, so let's rewrite that previous function to return a slice. So we let bytes equal s.askBytes. We check to try to find a space, and we return a slice from 0 to there, which is only going, it's not going to include the space. It's going to go everything up to the space. And if we don't do that, then we just return the whole string. Returning a slice also works for a second word function. Makes sense. Reference to stir. Is this... Okay, so this is actually, this is a predefined type, stir. Yes. So stir is the most primitive string type. It's usually seen in its borrowed form. Reference to stir is also the type of string literals. Reference to static stir. Okay. Gotcha. Oh man, that's a lot of documentation for a reference to stir. Well, for stir. Oh, it's a bunch of methods associated with it. Cool. Because the compiler will ensure that the references into the string remain valid. Remember the bug that we had before? So it was when we cleared and then tried to index something after it was cleared. So slice makes this bug impossible. So let mutable string, let mutable s equals string of hello world. Let the word be first word of a reference to s dot clear. Print line. The first word is word. So an immutable borrow occurs here, right? Because this is really only a read-only. This is a read-only slice, string slice. Or I'm sorry. This is an immutable borrow because it's just a plain old reference to s. It's not a mutable reference to s. Okay. A mutable borrow occurs here. And then an immutable borrow is later used here. So word ends up being an immutable borrow because this is not a mutable stir. And this immutable stir references something inside of here, but this changes it, and so it becomes a mutable borrow, because I suppose that this method is shorthand for passing in a mutable reference from s into this method, and then we try to use an immutable borrow here. And remember before how it was saying that you are not allowed to use an immutable and an immutable borrow or reference in the same scope. Right, so clear gets a mutable reference. Cool. String literals are slices. So the type of s here is a reference to stir. It's immutable reference to stir, or immutable stir reference. The slice pointing to that specific point of the binary. And it's why string literals are immutable. It's because its type is literally an immutable reference. Okay. So we can have a stir or a slice be an argument as well. Deref coercions. Yes, this is going to be what I'm going to read later on, because I was having questions about what it's doing here because it coerces the stir from the reference to stir. Right, so let's say we make a string, and then we can pass, we can do with this implementation, we can pass a reference to my string that contains the whole string, and thus we'll do the whole, it'll do the same thing as it did before. Or we can pass in a subset of the string. And it can also work, I suppose, through deref coercions with just a reference to string. Don't even need stir. And of course it works with the literal, which is a reference to stir, and that's what this is. Yeah. Yeah, cool. String slices, as you might imagine, are specific to strings, but there's a more general slice type too. Consider this array. You might want to refer to part of an array. We do so like this. Let slice equal reference to A from 1 to 3. Assert equality. Slice, which is a reference from 1 to 3, and a reference from 2 to a reference of 2, 3. Right, okay, so a reference to an array that just has 2 and 3 as its elements. So this 1 to 3 references this and this. And this should be true, because a reference to an array of 2 and 3 is the same as the slice. Bam. Running, asserts, cool. And all of this stuff, ownership, borrowing, and slices ensure memory safety. Cool. Probably the more complicated was references and borrowing. When we were getting over here, the rules regarding mutable and immutable references. This seems fairly straightforward. This I'm going to trip up on, I know it. This one seemed fairly arbitrary when I looked at it, but I think it'll make more sense. It's like, oh, why can't you have immutable and immutable? Well, because the immutable is expecting not to be changed. Right, the immutable reference is expecting to read the same thing always until it's done, whereas mutable is expected to change, right? So, okay. So pretty much a mutable reference means that it's getting a read-write reference, whereas a immutable reference is just a read-only reference, and so to have the both of them at the same time is sort of a contradiction. I can see that. All right. Yeah. All right, and so the next chapter is going to be structs. Cool. All right, so that's going to be neat. Yeah, I think I want to, I don't know how much of this book I wish to read. I want to get sort of a fairly good grasp of it from this book. I think I'll get to chapter 12. I think we'll do the project from chapter 12, and then I'll start doing my own stuff, and then here and there I'll read more. Right, I don't want to read this whole book, but I suppose I'll get through half of it, learn the basics of the programming languages, get to chapter 12, and then I'll start to do my own coding stuff, and occasionally I'll be reading this, but we'll do the first half of this book before we lessen the tempo, because I do have ideas of what I want to do with Rust. I want to, sooner or later, implement a hybrid of the Newton-Raphson optimization algorithm and I believe what's called the particle systems optimization, something like that. Particle swarm operation, right? Optimization, yeah. So I want to implement these. I want to implement a hybrid solution of it where it starts off doing the particle swarm, and then when it gets closer, and when it gets from a global, when it sort of finds the global minimum, it goes to Newton in order to exact in, because at that point you can treat it as a local optimization. That makes sense. So yeah, you see Newton-Raphson is based on a local quadratic approximation, whereas the particle swarm is more useful for finding global optimization, but tends to be slower in terms of convergence. So it'll be cool to use particle swarm to get an idea of where the absolute minimum will be, and then use Newton in order to hone in and get a precise match of where that global optimization is. So particle swarm is more coarse, and then you use Newton to fine tune your optimization. So I want to use Rust to do that, because these two are useful for Spice, because if we go to ng Spice, which is like the open source, and for those who don't know, Spice is a circuit simulator. It's mixed mode, mixed level circuit simulator. And if you go to documentation, go to the user manual. Oh, I actually prefer to go to the HTML page. If you go to here, simulating algorithms, blah, 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 blah. Convergence, circuit description. Where is it? Oh, it's before this. It was right after here. Convergence, yes. ngSpice uses the Newton-Raphson algorithm to solve nonlinear equations arising from circuit description. So yeah, it just uses Newton-Raphson. So I want to try to, I'm not going to say improve upon it, but maybe innovate upon it. Try to do something a little more original instead of just copying ngSpice. So yeah, I want to try to implement particle swarm with it, with Newton-Raphson, and then apply it to nonlinear equations and see how it works. And we're going to be doing it in Rust, and I believe we're going to do it after we're done doing chapter 12. So yeah, that's my plan with Rust so far. Alright, so I'm going to call this the end of the stream. I'm done with chapter 4. I don't really want to get started with chapter 5 until next time, because this looks like it's going to be just as long as chapter 4. But chapter 4 was a good size. It was just an hour and, well, fairly close to an hour 45. We're like an hour and a half. But yeah, should be the end of the stream then. Hope you enjoyed it. Here, let's see. Yeah. Cool stuff. So yeah, I think last stream I just pressed stop streaming and then I think I lost maybe a good 30 seconds or so of stream, so I'm just gonna put the outro overlay and then let it go until I see this come on, and then I'll stop the stream. Alright, well thank you guys for watching. I know there's not really a whole lot of people watching, but you know, I think it's good. I like streaming. I prefer to stream. I think it at least holds me accountable to be doing this stuff, right? Learning how to code with Rust and stuff, and having these little projects. So I'm glad, even if nobody's watching. All right. Well, that should be it. Time for the overlay, I guess. Thanks, guys, and I'll see ya later.